This is section 19.5 and this is about cell potential. So after reviewing what redox reactions are and exploring what voltaic cells are, remember the voltaic cells are taking advantage of a chemical reaction to produce electricity, and that electricity is measured as a cell potential. So now we're gonna see how you calculate those cell potentials given a particular set of redox reactions. So now to measure those cell potentials, remember that a redox reaction, you have one oxidation reaction and one reduction reaction that happen simultaneously, right? But in order to be able to measure the cell potential of the cell, then you need a reference. So reference should be just one of the reactions, but you can't really measure one reaction, meaning with the reduction reaction or the oxidation reaction, you cannot measure one of them individually. You are always measuring both. So it's necessary to have a reference based on which you calculate the potential for each reaction. And the convention that has been adopted to do that is to use a standard hydrogen electrode, and that is a particular reaction that we use to for this matter. And since it's standard hydrogen electrode, and we usually see from the point of view of a reduction, then we are talking about this reaction. We are talking about the reduction of the proton in solution to yield hydrogen in the gas phase. Okay, so that's particularly the reaction that we are looking at, and we are saying this particular reaction, or half reaction to be more specific, has a potential equal to 0. And every potential for every single half reaction is measured based on the hydrogen electrode. So the hydrogen electrode is your reference. You set it to 0 and measure everything based on that electrode. How does the standard hydrogen electrode looks like? Remember, we are using hydrogen in the gas phase. Okay, and we are assuming that it is measured at 1 atmosphere, and because it's a different phase from the solution, remember there has to be a transfer of electrons between the hydrogen gas and the hydrogen in solution, and the way you transfer those electrons is through a surface. In this case, because the hydrogen is a gas and you don't have any solid participating in that reaction, then we use a platinum electrode to provide the surface in which to provide those electrons. Now, for all single half reactions, we always look from the point of view of the reduction. Even if the reaction happens as a oxidation, those potentials are measured as if it was a reduction reaction. And when you find these values in tables, they are referred to standard reduction potential. And the real meaning of that is that you are measuring that potential under standard conditions. What are the standard conditions? Well, if you have solids or liquids and you are using them as a pure substance, which is not exactly a big deal, okay? Solid can easily be managed as a pure substance, same thing with the liquids. But when it comes to anything that is in solution, then standard conditions for that solution has to be 1 molar solution. Alright, so those standard electrode potentials that you see tabulated, they refer to conditions in which if you have something in solution would be 1 molar, and if it's something in the gas phase, like in the hydrogen, in the reference hydrogen electrode, then that gas is measured at 1 atmosphere of pressure. Okay, and thing to notice here, when you are referred to standard potential, you have the little circle here. Okay, so this is standard potential, and if you have just the E referring to to potential, then this is potential at different conditions. What does different conditions mean? Well, if you have a solution and the concentration is different from 0.1 molar, let's say if it is 0.05 molar, then that is no standard condition. That qualifies as a potential that you're measuring in non-standard conditions. Same thing for gases. If it's different from 1 atmosphere, then that is conditions, non-standard conditions. Okay? So, and then the standard reduction potentials look something like this. Okay, I want you to notice that every single reaction here is written. Let me highlight where the arrow is. Okay, so they are all written as reduction reactions. And why are they written as reduction reactions? Well, so that you can compare the reactions more easily. Okay, what does that mean? Well, this table is also showing you a trend in terms of different values that you have, or different electron reduction potentials that you have for each one of those reactions. Okay, so pretty much if you have, as you notice here, in that direction becomes more positive, and in this direction becomes more negative. Okay, and I advise you to always look at from this point of view. So whenever you have a table, always arrange it from more positive to less positive or more negative, because the meaning that you have there is that a more positive reduction potential means that the reaction is likely to happen as a reduction, which is already written as a reduction. But the more positive is the potential is, then it's more likely that a reaction will happen as a reduction. In the other hand, the more negative here means the reaction is likely to happen as an oxidation, which is the reverse, right? So if it's written as a reduction reaction and you have a potential that is more negative, then that reaction is actually more likely to happen in the reverse direction. Okay, so that is for now, that is the meaning that you have to see those potentials from that point of view. Okay, so when it comes to calculate the cell potential, then you remember you have a cathode, you have an anode, and then remember in the cathode you have the reduction, and in the anode you have the oxidation. Okay, now based on the standard reduction potentials, the reduction reaction would be the more positive value, and the oxidation will correspond to the more negative potential. It doesn't necessarily have to be that one is positive and the other is negative. Both can be positive, both can be negative, but then you have to rank them according to in what position they are. So if we take a look at these two reactions here, okay, so this one is more positive, and this one is, well, it's negative, but it's, let's identify it as more negative. Okay, so that means that this one, the first reaction, because it's more positive, that is going to be your reduction reaction, and this one, it's going to be your oxidation reaction, but it's not written as an oxidation. So that means that there's a reaction, instead of happening as written, you have to sort of invert, because it's, remember, if it's more negative, if you combine these two and you have one that is more negative, then the one more negative is more likely to happen in the reverse direction. So what is really happening here is that nickel will oxidize to nickel 2 plus 2 electrons. So this is the reaction that will actually happen if you combine these two half reactions. Okay, and in order to determine that potential, then is the cathode, if this is the reduction, okay, this is happening in the cathode and this is happening in the anode. So the potential here is going to be your cathode, which is 0.77, minus your anode, which is minus 0.26. Alright, and this is equal to 1.03 plus 1.03 volts. Okay, so that is the potential for that cell. One thing that I want you to notice here, when you are doing this, since you are doing everything under standard conditions, as of now, I want you to notice that here you have 2 electrons, right? But in the other reaction you only have 1. So technically you have to multiply the first reaction by 2 to balance the number of electrons. But you leave the potentials, you leave them out of that story. They don't need to be multiplied by anything. You select what your reactions are, you have the potentials, you assume that everything is under standard conditions, and then you just subtract those potentials. That's it, no need to multiply by anything. Okay, so here let's add that note. Do not multiply to balance electrons. Okay, if you want to balance the reaction, then yes, by all means you have to make the number of electrons equal, but if you are calculating the potential, do not multiply potentials. Okay, so you leave it alone. So one thing also to consider here, remember here, if you go up, the reaction most likely to happen as a reduction, and if you are going down, reaction more likely to happen as an oxidation. Okay, this depends on the relative position of the 2 half reactions that you are working with. Okay, now I want you to pay attention to this. Reactants near the top are powerful oxidizing agents. The reactant, so in this case fluorine here is the reactant, and fluorine is a powerful oxidizing agent, because it have a really high, relatively speaking, a really high reduction potential, positive reduction potential. Okay, now on the other hand, products near the bottom. Okay, so if you are going up, you look at the reactants, but if you look down, then you are looking at the products. Okay, so sodium, magnesium, aluminum, okay, they are powerful reducing agents. Remember, the oxidizing agents get reduced, the reducing agents get oxidized. So these here, they would prefer to oxidize to the ions instead of the ions be reduced to give you the metal. Okay, so that's why you are looking at the products as reducing agents, and you are looking at the reactants as oxidizing agents. Okay, so that you have an idea of how these elements or those substances are behaving within the electrochemical cell. So in this example, we are to calculate the potential and write the standard cell notation for a Daniell cell that is made out of the pair zinc 2 plus and copper 2 plus. And the thing that we have to do here is, well, let's locate these reactions on the table, right? So zinc is right here. Okay, so let's write that down. So we have zinc 2 plus 2 electrons that go to zinc solid, and the potential for this one is minus 0.76. And then we have copper, which is the copper solid copper 2 is right here, and that reaction is copper 2 plus 2 electrons go to copper solid, and the potential for this is plus 0.34. So this one is the more positive one. Okay, so this is actually your reduction reaction, and this one is going to be your oxidation reaction. Okay, so you're comparing plus 0.34 versus minus 0.76. Okay, so that means that if this is your reduction reaction, this is happening in the cathode and this is happening in the anode. Okay, therefore your standard cell potential is going to be equal to the potential of your cathode minus the potential of your anode, and this is equal to plus 0.34 minus 76 volts, and this is equal to plus 1.10 volt. Okay, so this is your standard cell potential when you combine those half reactions. All right, so let's rewrite everything again. In the cathode you have copper 2 plus 2 electrons going into copper solid, and in the anode you have zinc oxidizing to zinc 2 plus 2 electrons. Okay, if we are to write our standard cell notation, then I want you to notice here that you have copper solid and that you have zinc solid, so they can act as electrodes in this cell. So we start with the anode, and then we have zinc solid, okay, separated from a solution that contains zinc 2 plus, and then we have our salt bridge separating from a solution containing copper 2 ions, and then last but not least a bar of copper solid. So this is our standard cell notation for that, and this cell will have a voltage or a potential of plus 110 volts. What if we change the reaction? Okay, now we have a pair which is aluminum 3 plus, and aluminum 3 plus is right here. Okay, so that reaction is aluminum 3 plus 3 electrons goes to aluminum solid. The potential of this half reaction is minus 166, and then we have lead, which is right here. Okay, and that reaction is lead 2 plus 2 electrons goes to lead solid. So we have two solids here. Okay, so we can have electrodes made out of those metals, and the potential for the lead is equal to minus 0.13. Right, they are both negative, but actually this one is more positive. This one is more positive, or the other one is more negative. Let's write it down. So this is more negative. Okay, what that means is this one will happen in the cathode and this one will happen in the anode as an oxidation. Okay, so that means that your potential in the cathode is going to be minus 0.13. Your potential in the anode is equal to minus 166. Therefore, your cell potential is equal to minus 13 minus 166. And this is equal to 153 volts positive. Okay, so what is happening in the anode? Well, the oxidation of aluminum to aluminum 3 plus. So if we write our standard notation, okay, the anode is going to be aluminum solid separated from a solution containing aluminum 3 plus. We have our salt bridge separating from a solution containing lead 2 ions, and last but not least, a solid lead bar separating or in contact with the solution containing the lead ions. Okay, so this is our standard notation, and this cell will have a voltage of, or a potential of 153 volts. Now in this reaction we have a tin 4 tin 2 pair, which is right here, and we are combining that with chromium 3 plus chromium 2 plus, which is right here. Okay, right in the table, if you have that information, then you can simply say, well, this one is on top, this one is at the bottom, so this is your cathode and this one is your anode. So you pretty much will have the oxidation of chromium 2 plus to chromium 3 plus, and you're gonna have the reduction of tin 4 plus to tin 2 plus. Okay, so if we write those down, we have tin 4 plus 2 electrons go to tin 2 plus, and notice there is no solid involved in this reaction. The potential of this half reaction is equal to plus 0.15, and then we have chromium 3 plus 1 electron that goes to chromium 2 plus, and the potential for this one is equal to minus 0.41. Okay, based on this, the potential for the cell is equal, the more positive, which is plus 0.15, minus the less positive or the more negative, which is minus 0.41, and this is equal to 0.56 volts. All right, our standard cell notation. This is your cathode, this is your anode, right? So we have a combination of well, we don't have any solid involved in this reaction, right? So how do you provide the electrons? Remember, the electrons have to be provided at a surface. If you have a solid participating in the reaction, then that solid can be the surface in which those electrons are collected or provided, depending on what electrode you are working with. But if you have no solids participating in the reaction, you still have to provide a surface for those electrons to be collected or provided. So in this particular case, we can use platinum to provide that surface. And the platinum here is immersed in a solution containing chromium 3 plus and chromium 2 plus. Okay, they are in the same phase, so no need for a vertical bar, you use just a comma. Okay, so those two substances are contained in the same solution. Now they are still separated with a salt bridge from the other solution, and in the other solution you will have the tin and the tin 4 plus and the tin 2 plus. Okay, so you will have tin 4 plus, comma, tin 2 plus. And then here you also use a bar of platinum to provide the surface for the electron transfer. Okay, so this is how the cell notation for that particular cell looks like. Okay, so you will have as many vertical bars as different phases you have. In this case, you only have a solution and the platinum bar. All right, but if there was a gas, then you need another vertical bar separating that phase. All right. So, and all of this is to just give you this equation, which is the main equation in which you're gonna calculate the standard cell potential. And I want to stress the fact that you are calculating with this, you are calculating standard reduction potential. So for that cell is the standard reduction potential that you're using. And remember, the main thing here, for solids and liquids, no big deal, but for solutions, we are talking about 1 molar solutions, and for gases, we are talking about gases at 1 atmosphere. So that this is very important. Those numbers that we just worked with, they refer to using solutions that are at that concentration in gases that are at that pressure. Okay, now this is also very important. We have so far in all these cells that we have calculated, we have obtained a positive cell potential. Will that be always the case? No, it's not always the case, but if you obtain a positive potential, that refers to a spontaneous reaction. Okay, so that reaction will happen without you doing anything. When you connect them properly, the reaction will occur. Okay, now if the potential that you obtain is negative, then the opposite is true. The reaction is not going to happen. It's a non-spontaneous reaction, and more likely, in order for that to work, then you have to provide the electricity. So you are not obtaining electricity out of that electrochemical cell, but you have to provide the electricity for that reaction to happen. And most likely in those cases, if you have a non-spontaneous reaction, when you look at those potentials, probably what you are looking at is an electrolytic cell. And in that electrolytic cell, nothing is gonna happen unless you provide the electricity. Okay.